Over 2,300 years ago, a Greek philosopher named Aristotle created something that would change human thinking forever. He developed the first system of formal logic, the rules that govern how we reason, argue, and prove things. Welcome to Propositional Logic, the foundation of rational thinking that started in ancient Greece and now powers our digital world. Whether you're a student struggling with discrete math, preparing for technical interviews, or simply curious about how logical reasoning actually works, this video is for you. I'm going to break down everything you need to know about propositions in the most engaging way possible. We'll explore what makes a statement a valid proposition and, just as importantly, what doesn't. By the end of this video, you'll know exactly what a proposition is and, most importantly, what is not a proposition. My name is João Sarubi. I have a PhD in computer science, and I'm a professor of discrete mathematics who specializes in making complex mathematical concepts crystal clear. Let's start with the foundation. A proposition is a declarative statement with complete logical meaning that can only have one of two truth values, true or false. It must have definitive meaning that we can evaluate. Think of propositions as statements that make claims about reality, claims we can either confirm or deny. Let me give you some crystal clear examples. 2 plus 3 equals 4. Is this statement true? Absolutely not. But here's the key. It's still a valid proposition because you understand exactly what it's claiming. You know it's false. But the meaning is perfectly clear. London is the capital of England. This is another proposition. It happens to be true, but even if it were false, it would still be a valid proposition because it makes a clear, testable claim. There is life on other planets. Now you might be wondering, but do we actually know if there's life out there? Excellent question. Here's the thing. We simply don't know, but what we do know is that either life exists or it does not. There is no middle ground. Either there is life on other planets or there isn't. That clear-cut binary nature is what makes this a perfect proposition. Sarah graduated this year. This too works as a proposition, but only if we are speaking about a specific Sarah, someone we can clearly identify. Why? Because the statement can be verified as either true or false. Now, let's look at a case where things get tricky. She graduated this year. At first glance, it might sound like a proposition, but unless we know exactly who she is, the statement remains ambiguous. We cannot determine if it is true or false, because we cannot even determine who it is about. So remember this. For a sentence to qualify as a proposition, it must be clear, precise, and testable. Only then can we classify it as true or false. Before we dive deeper, you need to understand the three fundamental principles that govern all logical reasoning. Number 1, law of identity. This principle states that each thing is identical with itself. In propositional logic, this means P is P. A statement is identical to itself. If a statement is true, then it is true. If it's false, then it is false. This might sound obvious, but it's the foundation of consistent logical thinking. Number 2, law of non-contradiction. A proposition cannot be both true and false at the same time. This is crucial. We can't have contradictory truth values simultaneously. Number 3, law of excluded middle. Every proposition must be either true or false. There's no third option. No maybe, no partially true, no middle ground. It's binary, true or false, period. How we represent propositions. In formal logic, we use letters to represent propositions. The most common convention is to use lowercase letters like P, Q, R, S, and T for propositional variables. General propositions without specific meaning, while uppercase letters like P, Q, R are often used for specific propositions or formula schemas. However, this varies by textbook and context. Some use only lowercase, others only uppercase. The key is consistency within your work. Let me show you some examples in action. Proposition P. 2 plus 4 equals 6. This is a valid proposition with a clear meaning and definite truth value. In this case, true, since 2 plus 4 equals 6. Proposition Q. John's house is yellow. Since we're talking about a specific John, not just any random John, this house being yellow is a verifiable proposition. I don't know if John's house actually is yellow, but when you specify John, you're referring to someone identifiable, so we can determine the truth value. Proposition R. An even number is divisible by 2. This is another true proposition. It's a mathematical fact we can verify. What is not a proposition? This is where it gets interesting. Now here's where many students get tripped up. Not every sentence is a proposition. Let me walk you through the most common mistakes. Incomplete statements. For something to be a proposition, it must have complete meaning. My room is beautiful. This has complete meaning. You understand what's being claimed, and it can be either true or false. Beautiful room. This is incomplete. Beautiful room what? We can't determine whether this is true or false because it lacks complete meaning. Noun phrases. Sentences without verbs. These are phrases that don't contain action words or linking verbs. The large gray elephant. This is just a descriptive phrase. There's no verb, so no claim is being made. You can't say whether this is true or false because it's not asserting anything. If this video is helping you understand logic better, smash that like button, drop a comment with your thoughts, and subscribe for more mind-bending content. Exclamatory sentences. These express emotion or excitement rather than making factual claims. Go Team USA! Can you say this is true or false? Of course not. It's an expression of support, not a claim about reality. Exclamatory sentences aren't propositions. Interrogative sentences. Questions. Questions seek information rather than state facts. What's your age? Or what day is today? You can't assign truth values to questions. They're seeking information, not making claims. Imperative sentences. Commands. These give orders or make requests. Help me. Shred the documents. Put the trash in the bin. These are commands or instructions. You can't say they're true or false. They're directing action, not stating facts. Statements with indefinite subjects. Here's a tricky one that shows up a lot in logic puzzles and exams. That person was seen at the crime scene. Wait, which person? If I don't know who that person refers to, I can't evaluate whether the statement is true or false. Without a definite subject, it's not a valid proposition. This is a classic trap in logic exams. If you see a statement with an indefinite or unspecified subject, it's not a proposition. However, there's an important exception. Mike loves football. He is my friend. In this case, he clearly refers to Mike. So the second statement is a proposition. But if he is my friend appeared alone without context, it wouldn't be a valid proposition. Open sentences, variables. X plus 2 equals 5. This depends entirely on what x is. If x equals 3, then the statement is true. If x equals 1, then it's false. Since we can't determine a definite truth value without knowing x, this isn't a proposition. The truth value depends on the variable. Self-contradictory statements. Paradoxes. This is where logic gets really fascinating. Let me tell you a classic story that perfectly illustrates this paradox. A man was captured by a tribe who gave him an ultimatum. If you tell the truth, you will die by hanging. If you tell a lie, you will die by burning. The man thought for a moment and then said, I will die by burning. Now, let's analyze what happened. If his statement is true, he will indeed die by burning. Then according to the rule, truth tellers must be hanged, not burnt. So he should die by hanging, making his statement false. If his statement is false, he won't die by burning. Then according to the rule, liars must be burned. So he should die by burning, making his statement true. This creates a logical impossibility. The tribal chief had no choice but to let him go free, because neither punishment could be logically applied without violating their own rules. This statement is false. If this statement is true, then it's false as it claims. But if it's false, then it's actually true, since it correctly states it's false. This creates a straightforward contradiction, an assertion of both A and not A, violating the law of non-contradiction. Here's the debate. Some logicians argue these aren't valid propositions at all, since they can't be assigned truth values consistently, while others consider them unconditionally false propositions that are still propositions. For practical purposes in basic logic courses, treat self-referential paradoxes as not being valid propositions since they break our fundamental logical principles. This circle is square. If something is a circle, it cannot simultaneously be a square. This is logically impossible. But this is different from paradoxes because it's simply a contradiction, not a self-referential loop. I'm awake and asleep at the same time. You cannot be both awake and asleep simultaneously. This violates the law of non-contradiction. Classic example: the sentence within these quotes is a lie. Another paradox: when you encounter self-referential contradictions like this, remember, they're problematic for standard propositional logic. What's coming next? In our next video, we'll dive into simple propositions versus compound propositions, where things get really exciting. We'll explore how to combine propositions using logical operators like and, or, and not. Don't forget to subscribe and hit that notification bell so you never miss our logic tutorials. Trust me, once you master these fundamentals, advanced topics like truth tables and logical proofs will be a breeze. Drop a comment below. What's the most confusing part about propositions for you? I read every comment and use your feedback to make better videos. See you in the next one.